So for today's sessions, we're privileged to have Dr. Sorab Panday as our guest presenter to discuss the theory and fundamentals of MODFLOW-USG. Sorab really needs no introduction for many of you. He's a principal engineer with AMEC in Virginia in the US and is the lead author of the MODFLOW-USG code. Sorab has more than 20 years of experience in water resource and contaminant transport modeling, and his expertise includes the development of many simulation modeling codes and customized solutions for groundwater flow and contaminant transport. And Sorab is also an adjunct professor at the University of Waterloo. So the webinar today should take approximately 45 minutes. We've allocated a few minutes at the end for questions. If you're new to Webex, as shown on the screen there, you can use the chat feature to send a question. If possible, please leave these until the end, unless there's some technical difficulties. And we will make a recording available for download from our website in the next few days. So with that, I'll turn the microphone to Sorab.
Hi, good morning. I just need to get this to move. There we go.
There we go.
All right. Today I'm just going to talk a little about fundamentals and applications of MODFLOW-USG, and my co-authors are Chris Longevin, Rich Naiswanger, Joe Hughes, and Mutumo Ibaraki. MODFLOW-USG, it is finally out. So it has come out in April. It's available from the USGS website, and this is how the cover looks. So why MODFLOW-USG? We designed MODFLOW-USG initially to increase flexibility in grid design, add resolution where needed, handle pinched layers, handle things like offsets, allow for better solution of tightly coupled hydrologic processes, while still retaining the MODFLOW concepts and the general finite difference approach. So what is MODFLOW-USG? Essentially, it is MODFLOW with unstructured grids. It solves for three-dimensional confined, unconfined subsurface flow, has a variety of boundary conditions representing surface features, basically essentially all the boundary, a lot of the boundary conditions that are available in MODFLOW, and we will see those later. But it also includes additional features from MODFLOW, which is conduit and fracture networks. It has full implicit coupling of domains and Newton-Raphson linearization, so MODFLOW NWT features are available in MODFLOW-USG, and it includes some robust solvers. Finally, it has the framework for implementing other domains and processes. So for future versions, it is expandable. MODFLOW-USG has been created on the control volume finite difference formulation. So essentially, what is the control volume finite difference formulation? It is a generalization of the finite difference approach. In finite difference approach, you look at flow from a new node to its neighbor depending on Darcy law, which depends on the conductance and the head difference between the two nodes. So essentially, we've generalized the finite difference approach to look at all neighbors of node N, whatever those neighbors are. Benefits of this finite control volume finite difference formulation is that it provides this finite element flexibility. It is easy to understand and implement. Various cell shapes and dimensions are readily adapted. You don't have to have catalogs of cell shapes in your, for example, finite element codes. For each cell shape, you need it to be cataloged in the code, while here it is very general and you can adapt cell shapes easily. It provides robust and efficient solutions. It avoids element level integration in finite element codes, reduce nodal connectivities, nodal assembly instead of element assembly, which can be quicker, and it has a mass conserved formulation. CVFD formulation also allows you to have your discretization that honors geology. MODFLOW-USG uses prismatic cells in the vertical dimension. So in that sense, it can honor geology as well. Allows for tight coupling of other processes or domains. And by that, solution of tightly coupled processes, essentially, in MODFLOW, we used to be solving the groundwater flow process. Now, we also have a connected linear network process. And we tightly couple the two processes and solve both simultaneously in one matrix. So, when we build a matrix for the groundwater system, it's built. We add to it the connection terms for groundwater to this network, linear network. And similarly, you have rows for the nodes of the linear network. And we solve everything in one go. This also it gives you the framework for including processes or other domains. So if you want to add other processes, we certainly can. All we need to do is expand the matrix. This is possible because we are using unstructured formulation, because we are using unstructured solution schemes. Okay. So the processes and packages that are available right now in MODFLOW-USG are listed here. We support the basic packages for discretization, for flow, for hydraulic flow barriers. Upstream is not, it's supported, its capability is integrated into the VCF or LPF package. So in that sense, it's supported, the HUF package is not supported. Other than that, the transient boundary conditions are supported, the standard boundary conditions of MODFLOW are supported, the additional ones like stream, the stream with the unsaturated domain beneath, lake, gauge are supported, subsidence package is supported. And on the other side, these are not supported. The solver packages are not supported because the original MODFLOW solvers are structured and they cannot be used with an unstructured grid. But otherwise, the other packages are currently not supported and they may be supported in future versions. For instance, the ETS and DRT package, they've been useful. The MNW package is useful. New packages that have come in, instead of these solver packages of MODFLOW, now we have the new solver package, and it's just one solver package called the sparse matrix solver package. And within this are available several linear solver schemes. There are two essential linear solvers available within this, the PCG-U solver, written by Joe Hughes, and the ChI-MD solver, written by Mutamu Ibaraki. And both solvers have different solution schemes. They have symmetric solution schemes, PCG, preconditioned conjugate gradient methods for symmetric matrices, and they also have unsymmetric schemes like orthomin and BiCG stab. Excuse me, for unsymmetric matrices which come out of this upstream formulation and the use of Newton-Raphson linearization. Additional packages are a discretization package for unstructured grids. So, MODFLOW-USG is first of all fully backward compatible. You can use it with structured, we'll talk about that later, structured grids as well as unstructured grids. So if you have structured discretization, it uses the original discretization, but you have a separate unstructured grid discretization. Then you have this connected linear network package, and that provides you currently only circular conduits, but you have a network of connected line elements or linear cells which connect to each other and to the groundwater flow domain. And then finally, this GNC package, which is the ghost node correction package, which we will talk about a little more later. The groundwater flow process. As I mentioned, you can use a structured grid for groundwater flow. It is fully backward compatible with MODFLOW 2005, except for the solver package. As I mentioned before, the solvers cannot be backward compatible because we have a new solver package for unstructured systems. Grid is internally converted into an unstructured format. The solution is made and results are saved back in a structured format. So essentially, if you have MODFLOW 2005 data sets, with the packages that are supported, you should be able to run it right away within MODFLOW-USG just by switching to a new to the MODFLOW-USG solvers. And also you should be able to read back the binary files that are generated just with your regular MODFLOW 2005 binary file readers. You can use structured grid with the CLN process. So you can have this connected linear network. So these linear cells could be used as wells. So currently, since the MNW package is not supported, these linear cells can represent wells similar to the MNW package. However, right now it is fully implicitly coupled with the groundwater flow process and solved simultaneously. For unstructured grids, the groundwater flow process uses cell properties and cell connection information. So essentially, you have to let the code know the whole connectivity of the domain, so what every cell is connected to, and then for each connectivity, what is the area of the connectivity, what are the lengths, the separation distances between the cells or between the cell and the face. Cell numbers are used instead of layer row column. So when you are applying boundary conditions, for instance, instead of saying layer row column and boundary condition, you would be saying cell number and boundary condition. Solution is made and results are saved in an unstructured format. So you cannot read unstructured format output with your MODFLOW 2005 binary file readers. What are the discretization concepts for the groundwater flow process? Cells must be prismatic. So we do have in the vertical direction, we do have some structure in that sense. They are not tetrahedra. Cells must be convex. They cannot be concave. Grids may be simple, like you see here. It's a simple grid. Or grids may be nested, as in this figure where you see grids having nesting within a larger grid. Layering concept. The concept of layering is retained because it's easier for pre and post processing. We use GIS, which comes in as layers. So any layer you want will come into as one GIS layer, for instance. So you've separated out your output in those layers. You can have everything in one layer if you want to process it as such. So in that sense, the layering concept is retained only for convenience. Cells are numbered from top to bottom. Cell ordering, however, within a layer is not required. You can have any numbering within a layer. Each layer can have a different nesting structure, as you see over here, different nesting structure among different layers. And you can also have sub-layering. So within a layer, you can have sub-layers. Layers do not have to be continuous. You can just have this layer 2 is just something here, and then there is nothing over here, and you could have something else. So these layers, in that sense, are just for convenience of processing. Everything can be in one layer if you wish to process it as such. Grid types. Various grid types can be accommodated. As we mentioned, this is a control volume finite difference scheme. You are not limited to the grid types that are available within your code. There is no such thing as available grid types. You can be creative, but not too creative. There are certain grid error restrictions. We'll talk about that a little later. But grid types that are available, that is rectangular, your regular MODFLOW grids can be solved for. Triangles, hexagons, hybrid grids. You can have grids just with different hybrid structures. Irregular grids and Voronoi polygons. And these here are Voronoi polygons. This is a Voronoi polygon. And these Voronoi polygons essentially are derivatives also of Delaunay triangulations, which are used in finite element codes. So they provide a good complement to the finite element nodes of triangular cells. Nested grids can be provided. You can provide what are called quad tree refinements. So this is a quad tree refinement where it's refined only around features and not necessarily nested throughout the whole grid block. We'll talk about these rectangular grid types, as I said, because we come from the MODFLOW background. So to advance the MODFLOW background grids to the next level of grids, you have what are called layer structured grids. So it's structured within a layer. It's a MODFLOW grid within each layer, but as you go down layers, there might be a different grid structure. Reduced MODFLOW grids are just grids, MODFLOW grids, but where the domain is inactive, those nodes are just removed. So you have a reduced MODFLOW grid. And you have the local grid refinement, the LGR capability, where you can have your grid and you can have a subgrid within the grid. You have quad patch, where essentially what you are doing is you tell how each cell should be divided up. And like this cell, you say should be divided into four at one level. So you give it a level 1 and it does that. 0 level here, so it does nothing. 2 levels here, so it will take this cell and divide it into 2 levels, 3 levels and so forth. That's quad patch. And quad tree, octree are where you can divide any one cell into 2 different cells and into 4 different, and you continue doing that, and that's you can zoom in to a certain feature if you want, and that's quad patch or quad tree or octree. Excuse me. That thing came up here. Sorry about that. And this is quad tree or octree with smoothing. So you smoothen it such that one cell face does not have multiple cells on it, only 2. Like here, for instance, you have this having 1, 2, 3, 4 cells across this one cell's face. So you just smoothen it out, so one cell only has 2 cells on a face. And these quad tree, octree grid generators have become popular. They are available. The Voronoi triangle, Voronoi tessellations, the Voronoi polygons I mentioned earlier, they are also, there is a lot of work being done on that. They are being used by the gaming industry to create objects. And you'll see more of that later because Schlumberger is using these Voronoi tessellations for the visual MODFLOW Flex preprocessor. Okay, so CVFD has some accuracy considerations. I mentioned that earlier. Essentially, for accurate solutions, the line connecting the cell centroid should bisect the shared face at right angles. And that is why there is caution in using CVFD, that if you just use any old grid type, there could be errors generated because of the grid type you used. Regular grids hold this sort of property, so the line joining any 2 cells is bisecting the plane at right angles, at equilateral triangles, rectangles, regular polygons, as well as centroidal Voronoi tessellations. So essentially, when you are having centroidal Voronoi tessellations, the CVFD accuracy considerations are met. However, errors grow with deviation from this requirement, and that can have consequences related to cell grading. So it is not that it is wrong, but these errors grow with deviation. So you can deviate slightly from that requirement when you do cell grading, for instance. But then you're back to those old MODFLOW paradigms where you have to grade the cells smoothly. Irregular shape or nested grids also incur this error. So when we have nested grids, they incur an error because the line joining the 2 cells do not bisect the space at right angles. They do not bisect the face, and it's not at right angles, as you can see in this case. However, there's this generalized ghost node correction GNC package which is provided with MODFLOW-USG to improve accuracy. So what is this ghost node correction module? Essentially, flux between nodes N and M are computed by the head difference between head at M and head at N. That's the standard finite volume formulation. What the ghost node says, you should not use the head at N, but you should use the head at the ghost node location, which is the perpendicular bisector to the face, and that location then you can get the head at that location by interpolation between head at N and J. And that's what the ghost node formulation is to use head at N bar instead of N, and that the head at N bar can be obtained as a combination of head at N and maybe any of the J's around it in a generalized sense. And the optional formulation then, instead of using head at N, we plug in this head at N bar to give the flux between M and N. So this corrects for the errors that are incurred by the nested grids. It's an optional module because this correction may not be needed in lots of instances. For instance, the Voronoi tessellations, or if you are using grids that meet that CVFD property. This ghost node correction can also be used for location adjustment. For instance, your well could be located away, or your boundary could not be located on the cell itself. So we can always account for the head at that location instead of at the center of the cell by doing some sort of interpolation at that ghost location where you require the head, and then building the system of equations using the head at that ghost location rather than at the center of the cell. So when you have large grid blocks and you may just want to do a little adjustment for some boundary being not at the center of the cell, you can use the ghost node concept to do that as well. And an example of this ghost node correction for a nested grid, this is just a problem with uniform flow from left to right, and what it shows here are the errors in the solution. And you see that at the corners you have large errors in solution, and this is nothing to do with convergence, it is to do with the formulation, because we are not using the head at the ghost node location. It's the CVFD property being violated, and that is why those errors are there. However, in the center of the grid, those errors are down to the green range anyway, down to the 0 range. So the largest errors are where the grid is nested. However, if you go ahead and do the ghost node correction, you can see that those errors disappear. Here the scale is at E-7, while here the scale, the errors, there are 0.012 at the largest errors over here. While this is, the worst is 1.80 minus 7. Okay, so the connected linear network process, we haven't touched on that, but it has come up in the conversation, and what it is essentially this. We can have any sort of connected linear network of cells, the X's are the cells, and these can be superposed into the groundwater flow domain. They can be, these networks, they can be just wells. They can be a single cell representing a well, or multiple cells representing a well, or you could have adits reaching out from the well, or it could be a fracture network. They can be wetted or dewatered completely. They can be fully dry to fully wet. Right now, the current version does only laminar flow for cylindrical conduit features, but it can be extendable for other types of flow and for other types of features. And it can be used currently as an alternate to MNW, because MNW is one of the packages which is not currently available. Conduit matrix interaction is, the first point is that the conduit discretization is independent of the groundwater cells as far as MODFLOW-USG is concerned. That gives a lot of flexibility. So you can have multiple conduit cells within one groundwater cell or vice versa. It just matters on the connection and the area of connection of flow between one cell to the next. The connections themselves are done rather than through a leakage. Leakage option is available. However, the option that is also available is a modified time solution. So essentially, we are using this analytical solution, which has this logarithmic function for head with respect to the radius from a well, from a conduit, and it uses that to patch in the conduit to the porous matrix cell. The Pieceman function is used to find some effective radius where that head is at the porous matrix cell, and it works very well. We've done experiments with different cell sizes. The point being that you do not have to have finer grid discretization around the wells to capture the head at the well. We are using the analytical solution to capture the head at the well, and the well itself is represented as a conduit. And of course, the flow to dry cell option is also available. So it can be fully wet or fully dry. A skin factor, well efficiency considerations are taken into account, and anisotropy considerations are also taken into account. So if you have horizontal conduits, then this anisotropy is taken into account in computing this radius, this effective radius for the cell. Okay, when to use MODFLOW-USG? When you need the ability to focus resolution, for instance, where hydraulic gradients are high, near streams and wells, for example. Over here, you can just have a finer grid around your streams and wells and get your solution. To capture surface processes like the torch flow solution, you may just need finer grids near the top to capture those surface processes, and then you can use larger grids as you go down with depth. To capture detail, and that is where its big advantage lies. You could have in-step models, so you may have smaller models within a larger domains. You could have capture detail of partially penetrating wells, for instance, or partial flow barriers if you may have those. You may have local scale evaluations with multiple layers for mining or such applications, and the regional impacts may be modeled without having this fine grid going out to the large scale regional model, as well as without having the multiple layers if you do not have much information about geology to make such multiple layers. Just these finer discretizations may be just for the mine workings themselves. You may just have some resolution of input, for instance. You can have recharge or recharge ponds, and you may not capture it on your large grid. So you just throw in a nested grid around the region where you want to capture the resolution of that input. You could use it when you have layer pinch outs. Pinched out layers, you don't have to have the pinched out layers carried all the way across. Faults with offsets. The reason we can use MODFLOW-USG so readily is because of the finite volume connectivity. This cell 11 is connected to this cell 56 across this area with that separation distance. And at the same time, the cell 11 itself, the head of 11, and flow to 12 across this separation distance and this area between 11 and 12. So it's all a matter of connection. When you have well or conduit or fracture flows, MODFLOW-USG would be useful, and numerical difficulties with the regular MODFLOW because MODFLOW-USG uses the NWT formulation. So if you haven't yet moved on to using MODFLOW NWT, then you may want to just try MODFLOW-USG itself because you may have your old formulation as well as your new formulation working in the same code. Okay, that brings us to the ongoing applications of MODFLOW-USG. Essentially, the first part there was the formulation and what it can do, what the capabilities are. Currently, the USGS is applying MODFLOW-USG to very large-scale problems. This is the Los Angeles Basin model. It is by the USGS folks in collaboration with some others, I believe. This is a grid with pinch-outs. So they do have pinch-outs on the grids, and that is what they've been using MODFLOW-USG for. They started with a conceptual model and put the grids on top of the conceptual model, which they can do with MODFLOW-USG. Because block models can readily be converted to a MODFLOW-USG model. Nodes were connected vertically to nearest active cells, so when you had pinch-outs, they accommodated pinch-outs right away, and they used the CLN nodes for the pumping wells. Another application is this Lake Michigan Basin model by the USGS, and they are using the layer structured grid for this. It's a very fine grid. In layer 1, the spacing is 500 feet, and layer 2, the spacing is 2,000 feet, same in layer 3, and layer 4 is 4,000 feet. So it's a layer structured grid. The whole grid has 9 million nodes, and they couldn't really have got this finer discretization had they carried it all the way down. They wouldn't have, the problem wouldn't have even run on the computer. There'll be a paper coming out on this fairly soon, courtesy Daniel Feinstein. Then the USGS has applied it to the Biscayne Bay model, and what they've used here is the quad tree grid. So as you can see, this quad tree refinement was used around wells as well as along the canal features to refine the grid, and they had a MODFLOW 2000 model on a standard 50-meter grid, which they used for comparison. Well, the MODFLOW 2005 model existed, and when we generated the USG model, we used the MODFLOW 2005 model for comparison. So it had 1.6 million cells as opposed to 106,000 cells. The minimum cell sizes of both were the same, and this runs around 3 times faster than this. Memory requirements are much smaller for MODFLOW-USG and for MODFLOW 2005 for the same problem. The cells have been painted over here, so the large cells look blocky, but the heads are the same in the fine region of interest. You get the same heads where the grid is fine. The mass balance for the two models, as you can see, in blue is MODFLOW, and in this reddish is MODFLOW-USG. Pretty much the storage in, constant head, river leakage, recharge, total in, storage out, they're pretty much the same. Okay, benchmarking USG with Voronoi grids and FEFLOW. This is an ongoing project, and the FEFLOW benchmarking has not been done, but this has been done with the Visual MODFLOW Flex processor, which is currently it's almost ready there. Wayne will talk more about that, but the Voronoi grids are there and the MODFLOW 2005 grid, and those comparisons have been made. The FEFLOW fine grid also has been made, but I think they are doing some additional comparisons, and you can see pretty much you get the same results with all the grids. Another example, which is an ongoing project at Schlumberger, is this. This is a big watershed example, and it's a regional scale, 6 layers, and they are converting the model right now. It's a MODFLOW 2005 model, and it runs just a lot faster with the Voronoi triangles as with the MODFLOW 2005 finite difference grid. There are some slight discrepancies in total in and total out, but that could be also because of the blocky nature of the finite difference grid. And it's again work in progress, and they are looking more at what's to be done with that. Another application is this open pit mine dewatering. This is an AMEC Burnaby application, and here's the mine. That is the model. So you can see how much of the model was required, because there are some features over here. There are the river features over here which needed to be included to the east as well as over here to the west. So the impact of the mine on these river features could be evaluated. And even the mine pumping inflows could be evaluated. So this is an example of the mine inflows, and they're spiky because the mine plan was advanced on a yearly basis. Legacy MODFLOW conversion, one of our AMEC Irvine projects, a MODFLOW model with small regions of interest. This was the legacy grid, and this is now the MODFLOW-USG grid. The old run took around 21 minutes for the steady state run to run. The new one takes half a minute. The cell sizes, 1.3 million cells on this legacy grid and 130,000 cells on the new grid. And the sizes of the output files, the head binary output file is 500 kilobytes versus 5 megabytes, and this is the difference for the cell-by-cell flow term files. The transient simulations are much bigger because we have 45 stress periods, and if we even right at the end of each stress period, multiply each of these by 45, just importing those files takes forever to even look at them. But now, file sizes are just much smaller, and it is much easier to handle. AMEC Shrewsbury in the UK, they are working on a project for Southern Water, and the design exploratory stage models are what I'm showing you. There's a quad tree refinement around this river system and this large abstractions over here next to the river, and these abstractions are done using adits. So they would have this central well, and they'd have these adits at different layers pushing out at different angles into the domain, and they are using the CLN package to model the adits. And as you can see, when it's pumping, the CLN heads are below the groundwater cell heads, because these are representing the heads within the adit itself. And over here, what we see is that because of very little head loss in the adits, the flow field is wrapping itself around the adit. Just seeing it in different directions. Okay, so MODFLOW-USG supporting software. The USGS itself is supporting it with zone budget for MODFLOW-USG, and ModPath is something that will be coming. SSPA is supporting it. We'll see that. PEST Utilities are there, and the GUIs are available, including Visual MODFLOW Flex. Zone budget is already being distributed with MODFLOW-USG, and it's available on the website, on the USGS website. And if you are using structured grids with MODFLOW-USG, then you should use the original zone budget, because as I mentioned, if you are using structured grids, you should use everything to do with MODFLOW structured grids. ModPath is under development, but as you can see here, Dave Pollock has it working already. He just needs to get it cleaned up and documented. ModPath 3DU from SSPA is either already available or very, very close to it. All grid types are accommodated, while I should have mentioned that Dave is working on these rectangular type grid structures, so essentially nested grids or quad tree or layer structured or those rectangular grids I mentioned earlier. This can accommodate all types of grid structures. There are different tracking algorithms and can delineate unique capture zones for multiple CLN wells in a single cell. PEST utilities are available. There's a parameterless preprocessor, so you can use unstructured grids with your test runs as well as general interpolation tools. So you can take advantage of those unstructured grids with your PEST runs. Say, if you are doing pilot points for and regularization for your model inversion. The MODFLOW-USG utility is also written by John Doherty, and there's a grid specification file for use with PEST and this grid display, and that grid specification file can be converted to VTK files for view with ParaView. Then Visual MODFLOW Flex is using, as I mentioned, the Voronoi tessellations, the Voronoi grids, and they are available from their website over here. You can do grid pinch outs with it. You can have discontinuous property zones, and tomorrow, not tomorrow, but the next session, Wayne will be having some examples for that for part 2. Tips on using MODFLOW-USG: essentially understand existing capability and issues, and that is just a summary of what I went through, but that is one thing we need to do is understand what the code can do, then automate pre- and post-processing of model data sets, then use coarser grids. So start off with something simpler which runs fast and then refine it. I think that is the way to get into MODFLOW-USG. It's an easier way than overwhelming yourself. And develop a parallel model with a structured grid, for example. That's one way of getting into it, and that's one way of testing out your models, as we've been doing here as well. Future directions is to continue making improvements to the code, continue with training, workshops, and support, support more existing packages, add support software. So the USGS is working on this grid generations utility software particle tracking algorithms, and further enhancements to MODFLOW-USG that are under consideration right now are also under beta testing are variable active domain and zone relaxation. So your active domain can be different depending on stress periods, or your material properties can be different depending on stress periods. Three-dimensional Richards equation, transport, dual porosity flow and transport, adaptive time stepping, then time series input instead of having input of stress periods, which we have in the flow and head boundary and CHD, but we are considering just general time series input for all sorts of boundaries. Parallelization, fully 3D anisotropic tensor, and customization as needed. Wayne?
Sure, I can talk about this slide quickly. So yeah, as Sorab touched on, the second part of the webinar will be next Wednesday, October 9th, 8 a.m. and 1 p.m. Eastern Time. When those of you that are on the line, if you registered, would have registered for both seminars. And in that session, we'll touch on how MODFLOW-USG is supported in Visual MODFLOW Flex, just elaborating on some of the examples that Sorab showed in the slides here. We'll do just a summary of the key features and a brief live demonstration. All right. I guess with that, we'll open the line for questions. I'd like to thank Sorab for a really excellent overview of the MODFLOW-USG concepts and fundamentals. The great introduction in, I guess, 40, 45 minutes. As mentioned, the second webinar will be next week. If you have any questions at this time, please use the chat option